Hello, welcome to part two of Achieving Buzzword Compliance, Data Architecture, Language, and Vocabulary. This is now about technological design. Yes, I'm back. Hopefully many of you have already seen part one of this presentation. Essential Strategies International is my company's name. And this subject of this presentation is the book I wrote, Achieving Buzzword Compliance, Data Architecture, Language, and Vocabulary. Now, when I talk about buzzword compliance, what do I mean by buzzword? Well, the data architecture field has many terms that have become fashionable. That is, as they sped, their definitions have become muddy, they turn into buzzwords. Others have their precise original meanings still. They have not yet become buzzwords. Let's head them off. Our assignment today, Achieving Buzzword Compliance, the state where each of us, that is to say both you as the viewer and I myself, both understands and agrees to the concrete meanings of terms, especially as used in the data architecture field. Okay, understanding what I'm presenting should be possible. On the other hand, if you don't agree with anything I present, please feel free to let me know. Unfortunately, because of this medium, you can't do that in person, but I do have an email set up specifically for this purpose, buzzword@davehay.com. And you can certainly also call me at that telephone number. One caution. For each of you, some of these topics will be quite familiar. Each topic, however, will be new to some of you. My objective: describe enough for novices to understand each term and how it relates to all the others, and perhaps for the more experienced to see the term in a new light. Of course, to learn any of these completely, other sessions will be required and real textbooks, and you're welcome to check out the bibliography in the Achieving Buzzword Compliance book. John Zachman came up with a framework for enterprise architecture, which is noteworthy for its recognition of the different perspectives that different players have in the way systems are developed and the way business architecture is developed. As perspectives, you begin with the executive. These are the people that are responsible for the identity of the business, and therefore the language is based on that identity, and the scope of any further activities will come from these people. The business managers are the people in the company that do the work. These are the ones responsible for the definitions of all the terms and language. The architect is the one who takes the rather chaotic morass of the business manager's languages and sorts them ideally into more coherent language that crosses departmental boundaries. All three of these perspectives are from the point of view of business. There is no technology involved. The second set of technologies are what we're talking about today. The designer is the database designer or programmer or network designer that takes the architect's view of what is the nature of the business and translates that into specifications for new artifacts. The technician then takes those specifications and turns them into real databases or programs or network configurations that you like. Now, the objective of the technician is to come up with something that the enterprise can use, and it's the enterprise that takes this product and instantiates it into something in the world. Now, the first buzzword we come across, of course, is data modeling, near and dear to our own hearts. Well, there are a couple of flavors for data modeling. The data architect modelers are concerned with the underlying structure of language used in an enterprise. This was the subject of the first presentation. These are business-oriented. The data architect designers are more interested in the design of particular kinds of databases. These are the technology-oriented. Which are you? As I say, the first presentation was more oriented towards the business-oriented people. Today, we'll be talking about technology. Okay, I'm older than you are. Stephen's past us is in conversation. Okay, Stephen, when you lived in dorms in college, did it bug you when your roommate talked all the time on his cell phone? I didn't have one. They didn't exist. What about when they Skype someone on his laptop? No laptops. What do you mean no laptops? And how did you Skype people? No Skype. How could you have no Skype? No internet for it to run on. Oh my. Dude, how old are you? Technology moved fast. Need some well-all for your maps stuff? Okay, from the previous session, the agenda was concerned with the context and, more importantly, proposed kinds of business data models. There are three. The overview model, which is from the perspective of top management. The semantic model, which is about the language as used in the enterprise. And the essential model, which is a distillation of the enterprise language into more general concepts that apply across departmental boundaries. Here we have the flowchart of what these things were. The overview model was from the point of view of the executive and was concerned with setting the scope for all the further efforts. It was concerned with business concepts, and the vehicle was Sketch, possibly on a whiteboard, a simple entity relationship model. Now, this overview model, which covered the whole organization, got split into different semantic data models for each of the sub-organizations in the company. This is from the point of view of business management, and it's concerned with semantics. Specifically, it's concerned with terms, concepts, and definitions. And the deliverables are an entity relationship model, an object role model, what the object management group calls the semantics of business vocabulary and rules, and the various flavors of the semantic web. Now, this set of semantic models that cross vary from organization to organization get distilled into what we're calling the essential data model. This is the architect's view, which is integration of the business owner's views. This is entity classes, attributes, and relationships to create a consolidated entity relationship model. All three of these are under the rubric of conceptual data model. So if you're talking about a conceptual data model, you may be talking about any one of these three things. Today, what we're going to go to is the logical data model. The logical data model is the engineer's view. This is in terms of the technology that we're concerned with. In the case of a relational database, this is tables, columns, and keys. In the case of object-oriented application, it's classes, methods, instance variables. In the case of XML schemas, it's XML tags. In the case of something else, it's something else. The etc. in etc. is very large. Okay, so what are we doing in this session? Proposed kinds of technologically oriented models. Logical design are structures that indeed reflect the business, but in terms of a particular approach to database design. Physical design is for vendor-specific configurations that account for physical constraints. Specifically, logical design. We have a whole lot of them to choose from. Relational, tables, columns, and keys. Dimensional, which is denormalized tables. Object-oriented, which is classes, methods, and associations. Data Vault is a simplified version of the relational model tailored to data warehousing. XML Schema is tags used primarily for communications. NoSQL, which is our instances and classes. These are for the big databases that are sort of too big for the relational models to cover. And again, etc. Physical design, we'll talk about when we get done with this. Relational design, we have two approaches. Start with conceptual model of the business. Or bottom up, start with representative sample data. In either case, once you've come up with a design, you have to denormalize it to account for expected usage. Starting with top down. We'll start with the conceptual essential model we talked about in the previous session. Here we have a person, organization. Note that the entity relationship model is concerned with entity types. These are all categories of things, not the individual instances. Party may be a customer in one or more contracts. Party may be a vendor in one or more contracts. Each contract may be composed of one or more line items, each of which must be for one and only one item. Now, an item is either a product or service. Note that product, service, person, organization, city, principal country divisions, call it state, country, and other area. These are the entities, or these are the categories that are of real things in the world. The supertypes are abstractions that are supersets of they're all the people in the world, they're all the organizations in the world. Party is either a person or an organization. There are products and services. An item is one of those. A geographic area is either a city or a state or province or a country or something else. Note that a party may be in one or more geographic areas. Geographic area may be the site of one or more parties. But that's where we came in from the essential model. The architect came up with this. Now, what we have to deal with, if we're trying to convert it to a relational model, is subtypes. A relational model doesn't deal with hierarchies like this. And we've got the party subtype, supertype, the items, and the geographic areas. We also have to deal with derived attributes. You may have noticed up here that the line item, which is part of a contract, has quantity, price, and value. The value is the quantity times the price. The price itself was inherited from the item, and there's over here the value of the contract, which is the sum across of all these items, and the value is also summed to come up with the total for the product or the total for the service. Okay, these all have to be addressed in some way in the relational model, one at a time. You have the price, value of the contract, and total sales day. Okay, generate a prototype design. This was done by computer, system architect case tool, and it made some assumptions. It converted all the entity types to tables. So you have party, contract, line item, product and service, also person, organization, and these kinds of organization. Note that, first of all, the attributes became columns. So you have all the columns of each of the tables. Now we're going to generate prototype design by converting the unique identifiers to primary keys. Here you see various columns identified as primary keys, from party to contract to line item to item. Now, relationships are columns that are taking the role of being foreign keys. So here, for example, the line item contract number through the relationship of part of picks up contract number out of contract. Similarly, the column item in line item through the relationship for picks up the primary key item ID. And over here we have two foreign keys for party name. One is through the relationship of to, picking up party name from party. And the second one is through the relationship of from, again, picking up party name. Now, derived attributes are shown, but the logic for implementing them is not shown. First is price, which infers the price from the product and service unit prices, and then the value, which is calculated from quantity times price, and then that value is summed up in contract as the total value for the contract. Note, by the way, that the programming coding for these implementations is not covered here. Note also that the software for generating a prototype design chose to show all of the subtypes as separate tables. So person and organization split up to all of these parts of organization, and an item as product and service. Later we'll have to figure out what to do with those. Now, the bottom up, we're going to start with representative sample data. Here are some examples of the sample data that we might have. There are forms, sample reports, and current screens. Here is a sample form. We have the registration form that we use to register voters in Harris County, Texas. Each form is describing a particular prospective voter, and you have the questions they have to answer correctly. Yes, they're a United States citizen, and yes, they'll be over age 21. And then the rest of it is describing the name and address of the person, things like birthday, telephone number, driver's license number, and so forth. And all of this are data collected about the prospective voter. And if this form is being filled out with a deputy registrar, that person tears this off, fills this out, tears it off, and hands it to the prospective voter so that if they don't get the card in response to this, they know who to call. But this is the data about the person. Now, sample reports, this is already close to what a relational table might look like. You have column names and you have instances. Whether this is properly normalized or not, we'll find out later. Current screens are, of course, what everybody starts with because this is how everybody sees data in their sort of public-ish form. But there's a lot of different things hidden in here. First, you have the navigation. This is how you call up this form on the network. Second, there is advertising, which is sort of extra information that is not central to the subject. The subject, of course, is the book being advertised. Now, there are two flavors of the book, which are two different kinds of things. And then over here you have the transaction, if you will. Okay, I choose to take paperback and I want to add it to the cart. And this is the action of starting the process of buying it. So the only data are contained here, and a little bit is contained here. You'll note, by the way, the 5-star rating for this particular book, which may or may not be of interest to you. Now, this process of normalizing the data, you have various levels of this. But first, what do you mean by normalize? Well, according to BC, you normalize, which is what you have when you don't need glasses, then you have normal eyes. Now, take a raw bit of data. We're gathering some about testing in the backyard, and we've set up rows and a bunch of columns. Note, however, that the columns are in repeating groups. Okay, you have basic columns, the sample, date, code, description, and these constitute the primary key at this form. But you have 1 and 2 and 3, and we have no idea how many, which means the repeating group is not very helpful structure. So to get to first normal form, we're going to get rid of this repeating group by making essentially one line per test. So the primary key is sample date and the material code and the test number. And if you've got 3 tests, then you have 3 rows. And so these are rows this way and not across. So each sample plus test is in a single row. Note, by the way, you have column material description, which is exactly the same value depending on the material code. So everything that is 3256 is pool water. And here you have 3256, which is pool water misspelled. Now note the fact that we're in a state that allows errors to crop in. And so to get rid of that particular kind of error, we want to go into second normal form, which involves taking the material code and description and putting that into a separate table. Material code is the primary key, and description is what is being described, and there are only 2 of those. But the point is that in the test, you have the code given as a foreign key down to this material table. So 3256 is there, 4267 is there. You'll note something else here, however, that in the non-key columns, you have test description. Every time it's an A, it says scripts, and every time it's a B, it says chemicals, strips and chemicals and so on. So that suggests that what you really want to do is a different table for test type with the type and description, and the type is a foreign key back up here in the test table. And so that gives you third normal form. Now there are further refinements in something called Boyce-Codd normal form, as well as fourth and fifth normal form, but those are beyond the scope of this presentation. If you're interested, check out Mr. Date's book, An Introduction to Database Systems. At the time of the presentation, it was the 8th edition. As of today, it is now the 9th edition. More than you ever want to know about how to do normalization. An observation. If you followed the top-down discipline of modeling, you would have provided the same result as the bottom-up normalization approach. For example, the things of significance that are being described here are test, material, and test type. These are the things that are interesting. Note that each attribute is an attribute of only one of those things. So these sample date, test number, test date, pH value are attributes of test. Material code, material description are attributes of material. Test type code, test type description are attributes of test type. Now we have the connection is that each test must be on one and only one material, and each test must be of one and only one test type. And on top of that, we have the fact that the primary key, a unique identifier in this case, of test is a combination of the sample date, test number, and this on relationship. And this is exactly the same thing that we came up with when we normalized the raw data. Now, whichever way you approach it, you want to follow up by modifying the design to the expected usage, that is to say, denormalize. First, we're going to have to deal with subtypes. Duplicate the reference columns as appropriate, which is to say hard-coding the infer attributes. And we also have to hard-code the parameters that we separated out to actual columns in the tables, and then combining tables as appropriate. So first, looking at subtypes. Here you had person and organization having a supertype of party, which was an abstraction. The choice we have as to how to implement it is we're going to have one table for person, one table for company, and then we're going to collapse the unimplemented subtypes as a single other organization. Now, this means that the party ID is inherited by both person and organization, and the organization attributes are going to be inherited by company and this collapsed other organization. Now, note that department has its own attribute that applies only to department. If we collapse all of this, we have to make clear that only departments and not government agencies or governments get the department number. So the result is in the person and company and other organization, then party ID is inherited. And then from organization, the name of the organization and the description of the organization are inherited by both company and other organization. And then in the other organization, you have the column department number, which is used only for those organizations that happen to be departments. So if the organization type is department, then there will be a value for department number. Now, derived attributes and columns. Derived attributes in the essential data model are going to become derived columns here. There are three kinds. The first is calculated. In this case, we have the value, which is the price times the quantity. Second is inferred, so the unit price. It's either the price per hour or it's the price per unit, both of which are inferred through the to buy relationship. Summarizations. Here we have year-to-date sales, which is inferred through the bought via relationship from value. So we're going to summarize all instances of value, all the line items that are bought year to date. And similarly, the value of the contract is through the composer relationship from the value column in line item as well. So this value is summed through composed of to value contract. It's also summed through to year-to-date sales. Now, this idea of computed fields that in principle are only evaluated when somebody asks for those fields suggests that if you do a query, it's going to require a lot of processing. In those cases where the calculation happens only once, when you save the data, then you can, in fact, as I say, save it. You don't have to calculate it dynamically. So, for example, the price and the value and the quantity are computed when you create the contract, is the value of the contract as a whole. So all three of these are computed when you create the data, and then they're stored. And anytime you want to ask for it, they're there. But if you do the total sales to date, you don't know from when you save it, and then next month you're going to save it and the total sales will change. So this is a dynamic column, and so there you want to wait and have it computed only when you ask for the data. Note that the program code that calculates those dynamically is beyond the scope of this presentation. Now, in the essential model, we chose to pull some of our attributes over as party characteristics. That is, these would have been attributes of the party or one of its subtypes, but we wanted them over here because they change and you want to add new ones and their values change. So these were put over here in the interest of sort of keeping the model more dynamic. However, when you normalize it, you turn it into a relational database, you're going to get rid of these subtypes, and some of these party characteristics should be over in party as hard-coded attributes. Now, understand that this party characteristic includes these possible characteristics from party and their subtypes. Party characteristic value is of a party for a particular party characteristic. So you get one of these for each combination of party and characteristic. Note, by the way, that the value is issued by the same or a different party. So the party may be from the company, the party may be from a government agency like the Social Security. These are the values of the party characteristic. Now, some party characteristics apply to people, some of them apply to companies, some of them apply only to governments. There is a constraint here that says this party characteristic must be appropriate, that is, the characteristic for this party must be appropriate for the party type that this party is an example of. For example, height only applies to a party that is, in fact, a person. So height does not apply to any of the organizations. Annual profit applies only to a company. So here you have some of the characteristics wind up being hard-coded. Height, weight, Social Security number, credit score are all characteristics of the person. And the organization has things like revenue, profit, and credit rating. And these have now been hard-coded into these tables. Now, if you want to add a new column to the tables, then that's more work. A new column to the tables, that's more work. But this is a decision they make as a designer. Now, if you are changing the normalized design, be sure to document what exactly changes are being made, what performance benefit is to be achieved, and what cost in another area will be incurred. So you make this change to get a great benefit here, that's going to make it cost something else over there. Okay, so much for relational. Now let's move over to dimensional. The dimensional model reorganizes the relational model to account for specific users in terms of what we're calling dimensions, which are navigation routes from particular reference entities. Typically, these are customer, product, and time, maybe others as well. The point is that in each case, there's a fact entity type that is the transaction that has a quantity, usually with a date and time for that transaction. So, for example, you have product sales. Each sale is of a particular date, of a particular store, of a particular stock keeping unit. So what product, where is it, and when is it are all characteristics, dimensions, if you will, of that particular sale. So let's turn that into a relational database. So the product sales are keyed on the store code, where, the year, month, and day, which is where and time, the stock keeping unit, what is the product, and then the actual quantity, which is the fact that is at the center of this. Here you have all the dimensions of, to get to the day of month. A date, by definition, is year, month, day of month. All of you throw quarter in because you may want to organize it that way. Geography is country, state, city, and the actual store. And the product is the name and the product. Again, dimension are time, geography, and product. Fact is the product sales. Note that each product sale must be identified by a point in time, a store in the geography, and one stock keeping unit product. Now this can be broken out so that you can see more clearly, okay, this date is in the context of a quarter, this store is in a city, a state, and a country, this product is in a group, a brand, or a product line. Now, you still have the root, so navigation is not too bad, but there are joins required, so it will take time to execute the root. You do, however, have the fact that you can have other data related to the state, other data related to the country, other data from the quarter, product groups, and so on. Here we have something about standards. We currently have 14 competing standards. 14? We need to develop one universal standard that covers every use cases. Yes, that's a great idea. Now we have 15 competing standards. Think AC chargers, think how you encode characters, think instant messaging, or also data modeling standards. Oh well. We are now going to move on to object-oriented. This is a completely different way of organizing data in terms of classes, methods, and associations. Object-oriented design originated in the 1960s as an approach to process control programming. The focus is on things or objects that are created as data artifacts and methods that operate on those artifacts. This deals explicitly with messages sent between objects. Now, there are structures of classification and composition that are the most important, and those are explicitly labeled, but they're the only structures that are. So object-oriented design is based on an object that may be anything. It may be technological objects as well, screen or cursor, or it may be business objects, either one. An object is an instantiation of a class. Class definition includes descriptions of its behavior. Associations within classes are not structural. These are not like relationships in ER modeling. They are the message paths between two or more classes. Cardinality is similar to that of entity relationship, but there are no foreign keys, and only recently in the UML were unique identifiers identified. Here we have an example of a UML diagram. You have labeled each of the boxes as a class, so they have class names for the boxes. Attributes are listed inside the classes. Note, associations are not structures, these are roles. So for example, contract deals with one customer party, whereas party is playing the role of being a customer party for a contract. It's playing the role of being a vendor party for the contract. Contract is playing the role of being the contract from or being the role of contract to. It's the roles play, it's not the structure. You'll see more about that in a moment. For each class, you have operations that class performs, implemented via methods. Note that each contract plays the role of contract for each line item. And then there are 0 or 1 line items that play the role of component for each contract. So 0, 1, or more line items play the role for a component for this contract, and exactly 1 contract plays the role for a line item. Now note, there is one specific symbol for that structural information of is it composed of. And this is the only place that shows up. And now, for our next kind of logical design, we'll take up data vault, which is a simplified version of the ER model for data warehousing. Specifically, this approach began as the modeling structure of a data warehouse. It expanded to become a system of business intelligence with components needed to accomplish enterprise vision in data warehousing. The creators were Lindstedt and Olszynski, and version 2 is in this book, Data Vault 2.0. Now, entity types in Data Vault are 3. The first is a hub, which is simply a unique list of business keys. And simply each is pointing to an underlying thing of significance to the enterprise. And these keys are stored along with the metadata. Each instance is a thing of interest. Link is a list of relationships, each of which is among 2 or more hubs. Each represents a transaction by which business is conducted. Each instance is a relationship. Satellite is where the data are collected. It's a collection of elements that describe either a hub or a link, specifically the related data that describe hubs and links, and here you're going to get the whole instance for every different source. Starting with a link in an information engineering logical model. Here we have a contract role, which is linking party and contract. That is, a role is played by one party and is played for one contract. Now, there are various types of roles, and it's described here 2 ways. One is as the subtypes of contract role. The second is as a single table, which lists those subtypes here. So each contract role is an example of one and only one contract role type. Now, this is what we're going to cover in Data Vault. The equivalent Data Vault looks like this. Here you have the hubs are contract and party, and you have the load date for the hub for party and the load date for the contract. The link is between contract and party, and the contract party role type is the reference data. Now, this is sort of playing the part of a rub. It is linked. There is one role type for each role, as with this foreign key, but it's reference. It's not strictly hub because it doesn't have quite the same things going on that the hub does. Note the satellites are describing, contract has a set of satellites for the number, sign date, terms, scheduled delivery date, and person has some person attributes, birth date, surname. Company has organization purpose, and other organization has organization purpose. Note that the satellites all have a load date and time. And so you can have any number of times that different data are loaded up against the same contract or party. And it's the history of these data that are what the Data Vault is providing. Now, the next thing is XML Schema, which is tags from XML. Now, XML was founded originally as a language to support communications. It followed in the path of HTML and had the same kind of thing. It was replacing a protocol for doing data communications that was way, way more complicated than what you'll see here. It is structured with tags. Here you have an example of a transaction for a product which has an effective date of April 2002, and it has 2 components. One is the product number, 557, and the size, which is size 10. Now note, product has an end product, and number has an end number, and size has an end size. Every single tag has an end tag that constrains the diagram. Now note that, so tag is any string of characters or it can be a complex set of statements that you see here. Sometimes it can have attributes, as you see up above. And the domain of each tag, as I say, is ended by the /. Note that this is about instances of, in this case, a product. Now, the syntax of this script is defined by an XML schema. Now, back in the old days, we had a separate kind of language for defining the syntax of the script called document type definition. It has its own syntax and its set of definitions, and was very clumsy to try to understand as long as understanding the XML itself. So an XML schema was defined a few years ago in terms of XML tags itself. So XML schema is, in fact, an XML script. And here you have an example taken from our product example from above. XSD schema is the first line of any schema. Note that XSD is the Q abbreviation for XML schema. So all of these start with XSD. Schema is the first, and there's an end statement, the / schema. And so that's the first and the half. Now there are three elements, as you saw. There were product, number, and size. I said product, number, and size were the three tags that were meaningful. And so each of these has a beginning and an end. Now product, you'll notice, is a type, product type, and we'll learn more about that in a moment. Number is an integer, and size has a type, size type, and we'll learn more about that in an instant as well. Complex type, again, this is the product type that we saw in product, is defined as a name product type, and it has a start and an end. And this is significant, and that is it's defining a sequence. That is, number and size have to show up in order. You have to have number first and then size after that. In addition, the attribute shown above is an effective date of type XSD date. So here you have sequence, which is describing two elements, and type defining the effective date and date. Simple type, remember that size type was a simple type, and that has specifically a restriction that this size will ultimately be an integer. But more than that, it will it has no less than 2 and no more than 18. So the value has to be between 2 and 18 of size. And take a look at our example again. There we had, as I say, 3 elements, and the product has an attribute of effective date. There's a complex type for number and size which controls the sequence. Is it the product number and the size have to appear in sequence. This is an attribute, as we said. And the simple type, the size type here, is that it's at least 2 and no more than 18, as the 10 files with that. The number has to be an integer. This is not going to end well. Now our last logical design is NoSQL. It is not only SQL. It's not getting rid of SQL, but it's just not only SQL. It's a category for dealing with very large, big data databases. It's less about how data are queried than about how data are stored, specifically non-relational. As with the semantic web, it starts with instances and infers classes. Types are document, key value, column-oriented, and graph. Each one now in detail. The document is more application-focused. It's basically just pieces of text. Indeed, in Merriam-Webster, a document is defined as a writing conveying information. As a category of data collection, this isn't very compelling. Examples from NoSQL literature cite it as being a super category encompassing the others. Thus, it could be any collection of data as text. And document databases allow for maintaining, adding, or deleting text. Examples may also be mixes of structure and content, such as JSON or XML itself. Key value. There are two columns, parameter, which is a key, and value. So instead of having a string of parameters going across horizontally, you have a long, skinny table, which is basically two attributes. It's not quite that simple because value may be more complex, violating the relational constraints. Different samples of this could be very elegant, or can we say this, messy. An elegant example is created by yours truly back in 1989, well before NoSQL appeared. Clinical research was a precursor to this key value approach. Clinical study consists of a set of patients who have an ailment, that is the motivation for the study, take a medication that is either a drug being studied, the target, or a placebo, which is like a sugar pill, which is the control. Each patient visits physicians, and a physician administers the drug, not knowing whether it's a study or the placebo. The patient visits the physician on a schedule, and the doctor records the appearance of the patient's health, including symptoms, or lack thereof, of the ailment in question. Case report forms. In the past, this is the way it's recorded on paper forms. Each visit form consisted of a variable number of blocks. Now, each block represents a category of data, cardiovascular, intestinal, and so on. Each of which, depending on the study and the sequence of the visit, captured either one or more numbers, one or more text columns, one or more notes, and thus for each study is a variable number of different data designs to be created. This was very kludgy. In 1988, enter Super Data Modeler, ta-da! The pharmaceutical company Parke-Davis contracted with Oracle Corporation to construct a more reasonable data architecture to support clinical research. Modeling went through several iterations, but each involved the executives and the researchers, and the result was comprehensive, but at its core was recognition that clinical data should not consist of tables with lots of attributes. Rather, you have the observation entity table, and it's identified by one study variable, or possibly one activity variable. There are other variables they see other than strictly the ones that are in the study. And specifically, it's for one visit by a patient. And the attribute of observation is a value. Now, each day's data, the long string of skinny rows, can be reorganized by a utility so that for each block you have a table and you string over the attributes this way. And that can be then dealt with by statistical software. But the organization of the underlying data is as you see here. Now we're going to deal with column-oriented. There's relational columns and rows, but they're not predefined. Each row has a key, as in relational architecture. And for that key, a column family consists of multiple columns, each of which may have one or more timestamp value. So here you have a column which has multiple values, each of which has got a timestamp. It's similar, but the column may have multiple values. Here you have an example of a set of addresses. Now, two of them are in the United States, two of them are in Canada. So Boise is in Idaho, Baltimore is in Maryland, and Idaho and Maryland are states. Now, Ottawa is Ontario, and Vancouver is in British Columbia, and this is a province. So you have a column that has different kinds of stuff in it. Same story with the postal area. In the US, it's called a zip code, and in Canada, it's called a postal code. And what you have is a column for postal area, but it has two different kinds of things in it. The thing about it is that this can now be extended. If we wind up gathering addresses in the UK, under National Geographic Area, you now have a third one, which is a county. And it's also called the postal code in Canada, but this would be called a Canadian postal code, and that would be UK postal code as a different format that is here. Columns may be added or deleted. The graph. Graph databases. In 1971, Dr. E.F. Codd introduced the relational approach to organizing data. This was to provide the least redundancy and to make it way more understandable than the network databases that were basically hard-coded, very difficult to maintain. This was technologically superior to either the hierarchy or the network approaches of the day. This is, for example, a relational model. And here you have, it's a party which has multiple subtypes. Party is vendor in a contract and maybe a customer in a contract, and the contract is composed of line items, which are items, and items may be either products or services. This is very elegant and nice, but it's if you want to do a query, you're in trouble, because if you want to look at, for this product, I need to see, okay, what line items does it appear in, what contracts, and who's involved. How do I find out how many products we sold? And there are a lot of joins. The nice thing about a graph database is that the elements are posted in instances of classes. Here the class is user, the class here is odor, the class here is item. And these are encoded here so that you can do a query going through the network without having to mash everything together. Now you'll notice that the language here is a little odd, and this, by the way, is from one of the textbooks on graph theory. But they're much better in theory than they are in language. For example, this says that this which was in August 16th is somehow previous to that which is August 8th. At least that's the way you'd read it. What you're supposed to do is read this as previous to that, which is not the way I would do it with that arrow. You also have that this order off your iPhone contains ice cream. If I want to put ice cream on my phone, I wouldn't like that. I certainly don't want to put Brussels sprouts on my phone, and I certainly don't want to put espresso beans in my phone. So contains is not a good terminology for this. Also, user is not a good name for this cluster. The classes are identified, and that's fine, as they should be. Relationship names could still follow the bar Alice standard. It'd be messy if this were in fact containing all of these things. If we just simply update it to follow Richard's and Harry's conventions, then Alice is the source of these, as said before, and she's also the source of this one, and the fact that it's most recent is a tag added to this description. And the one on the 16th is after the one on the 8th, and each of these is for the items that are involved. Note, even in the technological realm, intellectual integrity, which is to say use of language, is still important. And now we have the etc., which is Latin for and other, and the big team there is the cetera, the other. Now, as of them I'm speaking to you, this is December 1st, 2022. Next month, we may add all kinds of logical design to this. Along with antimatter and dark matter, we recently discovered the existence of doesn't matter, which appears to have no effect on in the universe whatsoever. Doesn't matter. Physical design. The physical data model, which is to say the design of the physical data model, is about how data are physically stored on a device. And here we're getting into the realm of the vendors themselves. We have an application, maybe a set of discrete physical databases. So the Oracle thinks it's a table, but half of it is in London and half of it is in Cleveland. Each of those is partitioned up into pieces, and again, the Oracle notation is to call those partitions table spaces. Other vendors might call them something else. And again, etc. The details of physical design is something that is beyond the scope of this presentation, I'm afraid. The object management group calls this the vendor-specific model. So who are these people, the data modelers? Well, you may have a semantic modeler. This is someone who understands the language of the business. Perhaps an architectural modeler, someone who is very good at identifying underlying patterns and getting at the fundamental structure of the organization. Or a database modeler. This is someone who designs databases and manages databases. The object modeler is someone who's really, really good at UML and object-oriented software. The key is, if you are hiring one of these, be sure to describe clearly what it is you're looking for. Don't ask for a data modeler when you're actually looking for a database modeler, and vice versa. Similarly, if you're looking for a job, be sure to position yourself correctly. Some additional sections in achieving Buzzword compliance. There's some description of the different modeling standards available, including definitions of terms in each case. Also, standards for aesthetics, naming conventions, and some other standards as well. And of course, the glossary. The whole idea of this book is that it's a glossary of language and vocabulary for data architecture. Now, there are some other appendices. There is, for example, a table of different data modeling formats, a table for syntax for object role modeling, and one other which I don't recall. And there is bibliography in several flavors. There's, first of all, an overall bibliography of all the terms in the book, but there is a specialized one for data modeling books and relational database books and other. Here you have Jimmy saying to his mom that he answered the phone. Daddy missed his flight, but I can't remember if he said he was hung up with a layover or laid up with a hangover. And yes, I wrote the books. In addition to the one we talked about, my first book was Data Model Patterns, Conventions of Thought, which turned out to be the first one in the field, describing a standard data model, describing a standard business situation. There were about a dozen situations that were the subject of that book. Then in 2011, I wrote Enterprise Model Patterns, which was those dozen plus a bunch more going into different levels of abstraction, including several for industries, including the oil industry. Now, in between, I had a book on metadata and a book on requirements analysis. Now, I was hanging out too much with the object role model people, and they were insisting that UML is the best thing around, way better than anything that entity relationship diagramming can do. And I said, no, it's not, because it doesn't do the same thing. It doesn't describe structure the way the ERD does. So I was compelled to write this book, which was a reconciliation between the two, which was expressing exactly what the differences were and why. If you're interested in purchasing this book, you have but to go to the publisher, technicspub.com/buzzword, and if you use this code, ABC30, you'll get a 30% discount. I want to thank you all for your patience. I know it's been a lot to cover. If you have any questions, please write or call. I have an email address specifically for this purpose, buzzword@daypay.com, and my telephone is always available. The good thing about this being a recording is that you can go back and replay any of the confusing things.